morning, everyone. Let's start our workshop. And as always, we'll start with a quiz. The first question is, what ADT is used at Grafali's Cafe? Stack, set, queue, or list? Well, obviously it's a queue. And I think you saw this question in one of the weeks already. What are the main operations of a queue ADT? Push, append, pop, serve. And the two main actions we can do with the queue is we can add an element to the queue, append, and we can also serve an element. What is the largest number of nodes in a binary tree of depth n? Log n squared, or exponential? And the only correct answer is it's exponential. Right? If it's a complete tree, we have depth n, and each time we split into two, we'll have an exponential number of nodes in total. What ADT is used at many airport check-ins? Stack, set, priority queue, or list? Yes, and the obvious answer is it's a priority queue, right? If you pay more money, you have higher priority. What are the main operations of the priority queue ADT? Sync, add, rise, or get max? Here we're talking about max heaps. And just like with the queues, we can add an element in the queue. So it's the add operation, and we can also get max, the element with the highest priority. Is this a binary search tree or a max heap? BST, max heap, both, or none? And it's max heap, right? If you check carefully the invariant, immediately at the root you can see that both children are smaller than the root. So the invariant of BST doesn't hold, because in the BSTs we need to go, if we go left we should have everything smaller, and on the right it should contain everything that is larger than the current node. But if you check carefully, each child has a smaller value than the parent. So this is a max heap. Is this a binary search tree or a max heap? this is a BST clearly. You can see the invariant of the BST holds, right? In each node, you check the children. So everything on the left-hand side should be smaller than the value in the current node. Everything on the right-hand side should be larger. What does the completeness invariant mean in heap? Nodes are added level by level. Nodes are added from right to left. Nodes are added to last level from left to right. The heap contains all 2 to the n minus 1 nodes. And there are two correct answers. So we add nodes to the heap level by level, starting from the root, and then each level is completed from the left to the right. This way we are guaranteeing that the tree is balanced. Why is the first item put in position 1 instead of 0 in an array-based heap? Clearly we just want to mess with you. It's Axiom's tyranny as always, or must be my mistake. Or Brendan says it's easier to compute parent and child nodes. If you know whose voice is in the recording, you should know the answer. Yes, so Brendan is right. It's easier to compute the indices of parent and the child. The worst case complexity of heap sort is linear, n log n, squared, or exponential. As the reading says, the worst case complexity of heap sort is n log n. It's yet another algorithm that you encounter in our unit where the worst case complexity is this beautiful n log n. And here is the leaderboard. The leader is different this time around, surprisingly. Who is Matthew? Congratulations, well done. And let's get started. So today we're going to talk about priority queues, and today we're going to see how to implement them using binary heaps. And in particular, we'll be talking about max heaps. But everything we say applies to min heaps as well. And as you will see in your future career, heaps are used many times, almost everywhere, where you need to deal with priorities. I have a list of applications here. So for instance, if you think of air traffic control, if you think of call centers, if something happens and you need some sort of emergency, your call will be treated based on priority. Emergency services, power grid management, if you think about traffic control, if you think about online advertising, depending on priorities, the requests are treated in a particular order, right? If you go to a hospital and you have a problem, medical situation, you'll be first asked what sort of situation you have, and depending on how urgent it is, you will either be seen by the doctor immediately, or you will be, sitting in the queue for a while because there will be other patients who need help more urgent than you do. So this is where priority queues come in handy. And in fact, when you think of queues, you almost always think about priority queues. And this applies to computer science as well. Today, the workshop is going to be, I think, lightweight as last time. So we're going to play with binary heaps, namely max heaps. And let me first, before we dive into the exercises, let me first explain to you what max heaps are. So you know what a binary tree is. Everybody knows that now. So it's a tree where each node, unless it's a leaf, has at most 2 children. Now I showed you last time that if you add an invariant, you will get a binary search tree. In max heaps, it's almost the same, but the invariant is different. In fact, we have 2 invariants with max heaps instead of just 1 as in BSTs. So the first invariant in the max heap is that it's called heap sortedness. It means that each node, if you look at any node in the heap, so the left and right children will contain values that are smaller than the value sitting in the current node. So this contrasts what you saw in BSTs, right? In BSTs, you go left, everything will be smaller. You go right, it will be larger. This is how you divide the search space into 2 halves. In max heap, it's different. So the element sitting in the current node will necessarily be larger than everything below it, if we're talking about max heaps. So in min heaps, it's the opposite. Everything sitting at below the current level will be larger than the value sitting in the current node. So this is one invariant, heap sortedness. The second one is called completeness. And basically the idea is that you start completing the heap from the root. So you add nodes from the root, and then you add one node, it will become the root. Second node will become the left child. And then third node will become the right child of the root. So basically you will start from the left-hand side of the current level, and then you will complete the level. And then you will start the next level. It's like when you write sentences in your notebooks, you write from the left to the right, usually. Obviously, depending on the language, but usually in English, you write from the left to the right. And then you complete the line, and then you start the next one. This is how heaps work. So this is completeness. So what it gives us is, it gives us the guarantee that at any point in time, the heap is necessarily balanced, right? Because we complete the current level, we don't mess up with the children, we basically just complete the current one, and only then we proceed to the next level. So here is an example of a heap. As you can see, both invariants hold. The second one is easy to see, because we see that there are 1, 2, 3, 4 levels. 3 levels are complete, and the last one is not complete, but we started from the left to the right. And the first invariant, sortedness, says that the largest element is at the root, and everything below the root has values smaller than the one sitting in the root. And you can check any other node, you will see the same invariant holds, right? So 3 is larger than all the elements below 3, 7 is larger than all the elements below 7. Also note that because of these 2 invariants, we can see that any subtree in the heap will be also a heap, right? This is a heap, and this is also a heap. If you check here, this is also a heap, 2, 0, minus 1. So this data structure is recursive in this way. Any questions? No? It's all obvious? Great. Let's proceed. Now let's think how we can implement this efficiently. You can implement this using, just the link structures. You can create nodes and play with them. It will work. But the best way to implement a max heap or min heap is to use an array. So if you know how many elements you're going to have up front, then it's easy to use an array. So how it works is that we create an array, we allocate enough memory, and then we put all the elements of the heap starting from index 1. In the pre-reading, you saw why index 1, not 0. But let me just remind you, if you start from 0, then the computation, like if you're looking at the current node, say 3, the computation of the positions of the children of 3 will be slightly more sophisticated. The formula will contain 2 operations instead of 1 or 2, depending. Sorry, let me rephrase this. So if we look at these 3, we know that the children of 3 sit at positions say this is position K, the left child will be sitting at position 2K, and the right child will be sitting at positions 2K plus 1. And if we start from 3 and we want to compute the parent, we would need to apply integer division. So this is K, and the parent 8 will be sitting at position K divided by 2. And so this gives us a smaller number of operations, if you think about this, compared to the situation when we start putting the elements at position 0, because the children will be computed using the formulas 2k plus 1 and 2k plus 2, so 2 operations for sure, and then the parent will also be computed in a more complicated way. It will not be enough to just apply integer division by 2. So this is why we start from 0. Yes, we'll lose 1 cell, but it's not a big deal if we're thinking about elements, thousands of elements in the heap. Everything is still clear, right? You are still with me? Or do you need a bit more of an explanation? All good. So again, heaps. We consider in our unit only binary heaps. They can be max heaps, min heaps, depending on the sortedness invariant. And usually we implement heaps with arrays. And the most important trick to remember is that we start from position 1 in the array. Otherwise, we will need to deal with the children and parent indices computation. So here we have the first exercise. You will need to play with binary heaps, namely max heaps, and you will need to implement a few methods. So if you look on the right-hand side, there will be methods that are missing: largest child, sync, and rise. Right? So rise and sync will receive an index k, and you will need to apply rise and sync operations on the binary heap. Before you start, let me explain how these operations work. So essentially, when you add an element to ensure that the invariants hold, you need to insert the element at the very end, right? So you look at the last level, and then you see what is the rightmost position still free in this lowest level, and then, did I say rightmost? Yes. And then you put the new element there, but this way you are violating the invariant. You don't guarantee that the sortedness invariance holds. So you need to kind of put then this node to the right position. So you will need to swap it with the parents until its value satisfies the invariant. And this illustration here shows how it works. And if we construct the heap this way, this is called top-down construction, because we add from the root, and then the second level, and then the third level. We ensure that the heap is complete, and then we kind of ensure that the first invariant also holds by rising the new node to the right level. I guess it will be beneficial if I show you how this works. I don't know, say you have, this is the root, here we have 5 and 7, here we have 4 and 3, no, we don't have 3 yet. And here we say we have, yep, we have 7, 3. This is a heap, right? So it's a max heap because the largest element sits at the top, at the root. And now we want to add element 8. To ensure that the second invariant completeness holds, we put it here at the lowest level. And then, so it's connected to this parent, and then our task is, well, we see that the invariant here, the sortedness invariant doesn't hold because 5 is not larger than both of its children. So what we need to do is we need to rise this up to where it needs to belong. So what we do here in the rise operation, we compare these two, 5 and 8. So we start from 8 and we compute the position of the parent. That's why we need the computation of these indices to be done efficiently. So we check that the parent is 5. So the invariant doesn't hold. And then what we do is we swap. We remove this 5 from here, and we put 8 here, 5 here. And then we check, are we done or should we continue? So we again are here, and then we check the parent of the node 8 is 7. And we compare 8 and 7. The invariant doesn't hold, so we need to continue this. We need to swap 8 and 7. And now we're looking at the root, and we can see that the invariant now holds at every level. So 8 is larger than everything below 8, 7 is larger than everything below 7, and so on. So we first add an element here, right? And then we rise it up. It goes all the way up to the right position where it should belong. So this is what you will need to implement. To make this work, again, you will need to compute the indices of the parent and children. So I showed you how the operation rise works. It's more or less easy, but a little bit harder operation is the sync operation, where you go the other way around. You go down. So you have a node you're looking at, sitting at some position, and then you need to move it below this position, and you need to determine which way to go. To ensure the invariant holds, you need to select the largest child of this current position. That is why you need to implement the method largest child, starting from some position k in the array, and the children are 2k or 2k plus 1, so you need to select the largest child and return this position. And then depending on which child is largest, the sync operation should perform similarly to rise, but you will need to basically swap this node, the parent node, with one of the children, the largest one. And then you proceed until the current position sits at the right place. Sorry, the current element sits at the right place. When do we need sync operation? Can anyone help me? So rise is important when we construct the heap. So we add an element and we then rise it to where it should be. And when do we need sync? Exactly, when we remove an element. So by removing, I mean we get the largest one. Basically, if we think in terms of the queues, we are serving the element with the highest priority, right? So we're deleting it from the heap. We delete it, and then that means we are destroying the invariant. We are putting something at the root node, and then that root node needs to be lowered and put in the position it should belong, so that the invariants of the heap are both satisfied. Let me know if I need to illustrate this. I guess I should. So again, we have this heap. We are applying getMax operation, which means we need to return this element 8. What normally happens, We take this 8 and we put it somewhere aside. We're going to return this. And to ensure the completeness invariant holds, we take the last element, 5, and we put it at the root. So this is how the heap will look like afterwards. So 8 is going to be returned here, and this is our heap now. The problem is that the sortedness invariant is not satisfied anymore. It doesn't hold. So what we need to do, we start from here, the element which breaks the invariant, and we need to sync it. So to sync, we need to check which of the children of 5 is the largest. Among these two nodes, the largest child is 7. And what we do then, we put 5 here and 7 here. So we swap these two elements. And then we check again, is our heap sortedness invariant broken still? So we're looking at this node now, and we can see that the invariant holds. So node 5 has only one child, 3, and it's smaller than 5. So it's all good, and we stop the procedure get max, and then we return 8. I hope it's clear. If not, please let me know. So this is what you will need to implement. You will need to implement largest child computation. You will need to implement sync and rise. And when you're done, you can check your solution by pressing check and mark, and you can also run. And what this code in the main section will do, it will ask you, and to enter the elements of the array or the heap, and it will then add them all one by one in this loop, and then it will print them exactly in the order of the array. Okay, let's spend, I guess, 13 minutes will be enough. Meanwhile, if you have questions, raise your hand, somebody will help you. Okay, 13 minutes have passed. Do we have a solution? Do we have a solution? Anyone? Anyone wants to help me? Even if you don't have solutions, it's okay. Remember that making mistakes is not embarrassing when you learn. If I make a mistake, that's embarrassing. But if you make a mistake, it's okay. Anyone? Come on, guys, you will not have this chance in 2 weeks. This is the penultimate workshop for you. Yes? Okay. So where do you want to start? Largest child, rise or sing?
I think rise.
Let's start with the rise.
Up. Yeah. So in
rise we have the parameter k. This is the index of the current node we're looking at, and our task is, to move it up.
So I did while 2 less than or equals to k less than equals to length of self.
Hold on a second. While what?
While 2 less than or equals to k less than equals to length of self.
Length of self. Okay. Yep.
And self dot darray. And so it's part of the while loop. The while condition.
Sorry, what is the index here?
K.
K.
Then larger than self dot darray of k divided by 2.
Mm-hmm.
Yeah, and I put this as part of the while condition as well. So it was that and this. Yeah.
Okay.
Then I swapped them with self dot darray k, comma self dot darray k divided by 2.
And you swap these two, right?
Yeah.
Okay.
Then I divided k by 2 afterwards.
Mm-hmm. Like this?
Yep.
Anything else?
That's all.
Okay, let's see. Well, the swapping is obviously correct because we need to swap. This follows the illustration. Hopefully, I clearly demonstrated to you. And this is also correct because we need to update our k. We divide it by 2. Let's check the conditions of the loop. So we proceed while this holds. K is within this range. However, I don't see why we need to do this. Like, k is getting smaller, right? It will not going to exceed length if it didn't at the very beginning. So I think this can be dropped because can only get smaller. And we check that the invariant doesn't hold, yes, and then we swap. So this looks correct to me. Yep, let's proceed. Let's go to the largest child. So we start from some index k. And by the way, before we do that, is this clear? Is the implementation of rise, clear enough? Or should I explain it? Explain it. Good. So again, we start, maybe it's easier if I illustrate it. No, it's not, because then we won't see the code. So how do we do it? We start from some k, sitting at the very bottom of the, let me do it anyway. Okay, let's create a new page. So we have our 5, 4, 3, 2, and 1. And say we want to add element 6. These are connected like this. And since we ensure completeness, we added the very end here. Yes, so we add 6, and our task then is to ensure the invariant holds again, because here it's clearly broken. 3 is smaller than 6, so what we need to do, we need to rise 6. And in fact, if you check the entire heap, 6 is the largest element, so it should be sitting at the top, at the root. So what we do, the rise operation starts with the index of 6. What is the index? So this is position 1, 2, 3, 4, 5, and 6. Right, so we start from k equals 6, and then we compute this. This is going to be 3. Yep. So we are looking at this node and its parent with index 3, this node, and we check whether the invariant is broken. So 3 is smaller than 6, so we need to swap these two guys. That's what we do. Let me just erase 3 and 6, and we put 6 here and 3 here. Now the invariant holds in this part. However, it's broken here, so we need to proceed. So the new value of k now is 3. So we're looking at this node. So the parent of this node can be computed as k divided by 2, so it's 1, because this is integer division. So we know that the parent of this node is now 5. And we check, does the invariant hold? No, it doesn't. So we have to swap them again. So we remove 5 from here, and we put 6 here. We put 6 here and 5 here. Now, we update k, right? So k equals 1, and we don't yet know this. We don't compute this yet. So if you check the condition of the while loop, it says while k is greater or equal to 2, which means at this point we stop the loop, right? So we know we are at the root, so we stop because we know, well, there is no parent of 6. We're done. Right? This is the condition I'm talking about. K is greater than 2 or equal to 2. Okay, good. Okay, let's implement largest child.
My implementation isn't as nice as the slides.
It's okay.
What I did is I said left index equals 2 times k,
Mm-hmm.
and then right equals left plus 1.
Left plus 1?
Yep.
Mm-hmm.
Then I say left child equals self.theArray bracket left.
Sorry, you're doing this?
Yep.
The array of left,
And
and
then
I guess right
yep.
will be... Okay.
And then I said if left child and right child
If left child
and right child.
and right child.
Yep. So it just checks that we have 2 children. Then I say if left child is less than the right child, then we return the right child, the right index.
Is it inside here?
Yep, inside here.
If left child is greater, you said?
Less than.
Less than right child, then you return the right child.
We return the right index.
Ah, right, yes, you return right, yes.
Otherwise, we can return the left index.
Uh-huh.
Yep. And then outside of this if, we can check if left child and not right child. So we only have 1 child, so we can just return the left index. It should be if left child and not right child.
Okay, yeah.
And I guess we could just return none otherwise.
Happens if you have a negative value.
You mean here?
Yeah.
Okay. So it's indeed a bit more bulky than I would expect, but let's check. So these are the indices. So this is 2k, and this is 2k plus 1. Hopefully this is clear to everybody. And here we check, so we save the left child and the right child. So we take these positions in the array, left and right, and we keep them in these two variables, left child and right child. And what the next code is doing, the following code, is we check if both of them are not none. Is that it? Is that the rationale? So you want to check they're not none, both of them. But what happens if you are outside the bound? Like the array is, one of these guys points to some position in the array that doesn't exist.
Well, I guess our precondition is meant to check for that.
Nope, it doesn't, right? So you start from some k and you increase k. You multiply it by 2. And at some point you may end up in a situation where there is, so this node doesn't have any children, so it's the last node, for instance, right? I don't know, somewhere here. So you are checking this, and left and right, you will compute these values, but the array doesn't have anything. It doesn't contain any, nodes. So essentially, the program will crash. I think. It depends on the programming language, but these conditions are not enough. Where is this? Where am I?
I think it's the previous exercise.
Previous exercise. Oh, yes. But anyway, the logic is clear. You want to check whether both children exist. In this case, you compare them and you return the largest child. And if the right child doesn't exist, you also return the left child. And otherwise, you return nothing. So let's try to construct a solution closer to the one you saw in the pre-reading. So it will be pretty simple. We will say if left equals length of self, this means there is no right child. Or self, the array at position left, is greater equal than self, the array right, we return left. Alternatively, we return right. This code does what you wanted to do here. And it always returns something. So largest child must return a child, a position. And the logic of this is that we won't call this procedure, this function, unless we're sure there is at least one child. So it shouldn't return none. Okay, so I think this should work correctly. Do you have sync implemented? Okay, let's try.
So you can do, while 2 times k is less than the length of self.
Less than the length of self,
So
okay.
while we still have a child, then we can say child equals self dot largest child of k.
Let me just add this comment that you added. We still have a child.
Yeah, so we say child equals self dot largest child bracket k.
Yep. So we call this procedure we've just implemented.
And then we check for the invariant if self dot the array bracket k is larger than self dot the array bracket child, then we can break because we are done syncing.
If self dot the array at child is greater than,
Okay, I guess less than in this case.
less than the array at k.
Yep. Then we can break out of the loop.
Then we break, okay.
Otherwise, we swap them.
Okay,
Just-
let me do this. I will put a comma here. We are swapping them. Swapping the current node with its largest child.
And then we update k to become the index of its child that we just swapped it with.
Like this.
Yep, and then that's done.
And that's done. Well, this looks correct to me. Let's check. It doesn't work. Why doesn't it work?
I think it should be 2 times k is less than or equals to the length of self.
Yes, that is true. Now it passes the test. Okay. Thank you. So this does work. So the logic of sync is exactly the opposite of rise. So we start from the root or at some node in the heap, and then we want to move it down. And in order to maintain the invariant, we need to decide which way we go, left or right. So we pick the largest child and we swap the current node with its largest child. Let me share the screen again. Okay, so let's say we have, oops. I don't know, let's say 3 is now here. So we start from 3, from the root node, and we want to maintain the invariant, so we need to decide where 3 should go. It should go to the level where it is smaller than all the parents. Right? To make sure that it all works, we select the largest child of 3. So this is our k. It starts with 1. So initially, k is 1. And the largest child, according to our procedure, will be 5. It should be element 5, but the value, the index of the largest child should be 3. So there should be this variable child we created. It will be 3. And now we compare these two elements, 3 and 5. The invariant doesn't hold, so we swap them. 5 is moved here, and 3 is moved here. Now the invariant holds, and we, in fact, our loop will check, it will update k, it will become 3, because we will say k equals child. And then we check, is 2 multiplied by k, which is 6, is it equal to length, sorry, is it less than or equal to length? And 2 to the k equals 6. As you can see, we have 5 elements, so the condition of the while loop is not satisfied. It doesn't hold, we break the loop, we stop. So by the end of this procedure, we know that we're done. We went all the way down. Okay, just one comment. So here we are swapping the elements. We are applying 3 equality operations, right? What happens here, we create some, you can think of this as creating some temporary variable and say it keeps self the array of k, and then we say self the array dot at k equals this, and then you say self the array at k over 2 equals temp. This is what in fact happens in this code, right? 3 times three elementary operations. Yes? To avoid this, we can just put the current element we're looking at somewhere aside, this one, and we will just update one of these elements, and here we will say temp. Oops. And after we're done, we can just say self the array at k equals temp. So essentially, it does exactly the same what we did before, but we're saving a couple of elementary operations. We just update the value sitting at the current element, and then at some point we will we will put this element that we put aside to the position, to the final position we computed. The same can be applied in the sync operation. So if I click check, it still works. I will not update this in the sync operation, but the logic is exactly the same. So we put an element aside, and then instead of swapping, we kind of moving the largest child up, and we are updating k. At some point, we will just say the current element must sit here, and we put it there in the end. I guess I can leave this as an exercise for you, as a homework. Okay, let me click run. So we have, I don't know, something like 3, 2, 5, 1, 4, 0. These are our elements, and then we create a heap, as you can see here, and then we add all of them one by one, 3, 2, 5, blah, 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 and then we're going to print the contents of the array. Yes, so the content of the array will be exactly this. The initial position of the array, the position 0, will contain nothing, it's none. And then our first element, the largest element, will be 5, and then there will be these children, 4 and 3, and then there will be children of 4, 1 and 2, and the left child of 3. Is this clear? Yes? Okay. I spent a bit more time than I expected, so let's spend now 10 minutes on the quiz, and then we'll proceed. Okay, time to move on. We don't have too much time left in this workshop, and we still have 2 exercises, people. So please get back to this. Bear with me till the end. Hopefully you will learn something new. So in the previous exercise, what we did, we created a heap, right? So we saw how to add an element by means of just adding it at the very end and then rising it up. We also saw how getMarks works. Basically, we just take the root, we put it aside, and then we swap it with the last element, which is going to be small, and then this last element, which now sits at the root, will need to go down, right? We saw how to do that using sync. This is all nice, but say we want to create a heap with this sortedness and completeness structure. What if we don't want to spend too much time? Because the previous solution, it was n log n. We can in fact create an array in the heap order in linear time. So the previous solution was called a top-down solution because we started from the root and we sank the elements to the bottom. And if we want to create, well, what I want to say is that we can do the opposite way. Let's see how it works. Let me share this screen. Something like this. Say we have an array 1, 2, 3, 4, and 5, and we want to make it in the heap, to put it in the heap sort order. So what we will need to do, we'll create another array where there will be, sorry, not 0, it will be none initially, 1, 2, 3, 4, and 5. This is what we do. This is a linear time operation. Basically, we just copy the content of this array to a new one, and this is where we're going to, the array we're going to play with, so we're going to make it in the heap order. You can see this array, that the one we created, as this heap. You see the invariant, the heap sortedness invariant is broken. Hello, hello, people. So we have this array, and we can see that the heap sortedness is broken almost everywhere here, right? So 1 is smaller than the children, 2 is smaller than the children. So it's not good, but what we know for sure is that since heap is a recursive data structure, we know that each of the leaf nodes are heaps already. So instead of just, you know, rising all the elements up, like what we could do is we create 1, and then we would add 2, and then we would rise 2 and swap the 2 guys, and then we would add 3, oops, and then we would swap these 2. Instead of doing this, we just create the array once, and then we go the opposite way. Because when we do this way, we know that each new element is going to spend a logarithmic number of operations in the worst case to go up, right? But if we go the other way around, so we have this array, and we, for instance, look at one of the nodes, 2, it doesn't need to go all the way down. It needs to go just one step down. Sometimes it doesn't need to do, we don't need to do anything. So we know these 2 are heaps, and now we're looking recursively at this heap, 3 nodes, and we see that it's not in the heap order. So we just start from these 2 as a root of this sub-heap, and we sync it. So, right? So we select the largest child is 5, and we remove 2 from here, and we put it here while 5 is there. Then we check this node. Well, it doesn't, it's a leaf node, it doesn't have any children, nothing to be done, so it's already a heap. Now, this is a heap, so this needs to become a heap as well, but 1 is breaking the invariant. It's smaller than both of its children, and what we need to do is we need to sync it. So we apply the sync operation. 5 will move here, 1 will move here, and then we apply the procedure again. We select the largest child, 4, and 1. This way we can also construct the heap. So instead of just adding elements at the very end and rising them up, we can just copy them to the array, and then we can sync the necessary elements. This way, the complexity of this procedure, the creation of the heap, becomes linear. The magic of the computation of how many elementary steps we're performing is shown in the pre-reading. I don't want to spend time doing this, but it's pretty simple to see. So if you are interested, please check that. But the beauty again is that instead of n log n time to create the heap, we spend linear time. Now, in the following exercise, we are going to implement this. So your task is to, where is that? It's here. So we want to implement this procedure called heapify. So we have some array. This is our input, an array, and there is some initialization done in the heap constructor. So we know what the length of the array is. It's self.length. Your task will be to implement that procedure I've just visualized. Heapify to use the bottom-up procedure. Let's spend 5 minutes on this. It's not very difficult. And then we'll construct our solution together. Okay, time's up. Do we have a solution for Hippify? No? Anyone? No? Okay. Okay, let's do it together then. So, we need to implement this procedure, Hippify. It receives an array, and our task is to create, to shuffle elements the right way, such that the array we are keeping inside our heap is in the heap order. Okay, Matthew has a solution. Great.
So first, I just added everything in an array into like self.array
Okay,
with
so
the enumerate function. So for I element in enumerate an array, self.theArray I plus 1 equals element, because
So
I plus 1, because
we are doing I
starting
plus
from-
1 equals an array at I, right?
Yeah,
So why do we use this I plus 1 here?
because we start counting from 1 rather than 0.
Exactly, right? So we need to make sure that the 0 element is none, because we need to compute our children and parent indices correctly. Okay, so this is adding all the elements in the heap. Okay?
And then set k to be length of an array truncated by 2, truncated division.
Like this?
Yep.
Mm-hmm.
And then just while k is greater than or equal to 1, just sync k, and then decrement k by 1.
Well, you said k equals then equal to 1, which is equivalent to this.
Yeah.
Okay? And then you do self
Yeah, just self.sync k,
self.sync at k. Yep.
and then decrement k by 1.
And yep. So this is the first step. Step 1. We're copying all the elements to the heap. Step 2. Syncing the elements that have children. And we know for sure that all the elements with indices larger than this, they don't have any children. Like if you check the prereading, if you play with the heaps, you see how the trees look like. We know that the elements that have indices larger than this, they don't have children. They don't need to be sank, right? So we start from this k, and we're going to go up because we are going to decrement k, but this element at position k will need to go down. And in the end, we're done. Well, it says this should be length, obviously. Now it passes the tests, and if I click run, this is the section of the code we're implementing. Let me just, uncomment this, run again, and I will do 1, 2, 3, 4, just like in my example in the drawing. And this should be the content of the heap. So the zeroth element is none, and then at the root we have the largest element. The left child is 4, the right child is 3, and then the last level will be containing only 2 elements, 1 and 2, that are children of 4, just like in that drawing. So why do we need this operation? Why do we want to spend linear time for heapifying instead of n log n? Can anyone answer this question? Some ideas. You see, we can implement heap sort by creating the heap in the right, with both invariants holding, and then we just take get max, get max, get max. In this case, if we implement heapify this way, so say we use top-down construction plus get max, we're going to spend, for the construction itself, O of n log n plus, well, plus get max will be done n times, so it's n log n as well. So the overall complexity of sorting an array with the top-down construction will be n log n. So what we are saving with this better implementation of Hippify, let me just copy this. Bottom-up construction will spend this time for sorting n plus n log n. But we know that n log n dominates n, so we're not saving, asymptotically, we're not saving anything, right? It will be n log n in both cases. So why do we need a faster Hippify? When does it come in handy? It comes in handy when you don't want to sort the entire array. Say you just want to, compute the largest 5 elements of the array. How do you do that efficiently? Well, you Hippify in linear time, so you compute or return the 5 top elements. You would spend linear time on Hippify using bottom-up construction, plus you will spend 5 times log n for get max. And now, n dominates the other half. Right? So this is where it becomes really efficient and nice. So you don't want to sort the entire array, but you want to sort a part of it. A constant number of elements that are the highest, the largest, you return them and you are done. This is where Hippify done in linear time comes in handy. Is this clear? Okay. Now let's implement heap sort, and this is going to be a trivial exercise. I don't want even to bother doing this, but let's spend, say, 3 minutes on this. Because it's trivial, we do Hippify and we apply get max n times, and you need to do it in the main section now. So you have this part not implemented, and your task is to output all the elements in the right order. The maximum first, then the second top, and so on. Okay, time's up. Do we have a solution? Yes, we do. Do we have anyone with the microphone? It's here, Phoebe. Yep, well, just wait a second.
Yeah, in the if statement, you just do for underscore in range heap.length.
So arrange.length, sorry, self.length.
Oh, no, heap.
Sorry,
heap.length.
heap.length,
Yeah,
sorry.
because that's out of the...
Let's do it in a proper object-oriented way. We will do this. It's the same.
Yeah, I know. And then you just do print heap.getMax.
Print, sorry, what? Heap,
Heap.getMax.
get max. Yep,
That's it, right?
yep, it does work. Well, I mean, the implementation, we didn't change anything. And now if we click run, you see we have this array 1, 9, 12, 5, 17, 15. And this, this code, well, first it creates the heap, and then it prints all the elements in the order they are sitting in the array. Yep. Well, it's, hold on a second. Because Heapify prints too much. Let's not do that. Verbose equals false. Now run. It's still... Okay, let me just... Okay. Yeah, now it prints twice. So what we see here, we first print the content of the array, none, 17, 9, blah, 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 all the elements, and then we run this while or for loop n times, and we get the maximum element. So each time we do this, we apply a logarithmic number of steps to print this, this, and so on. So if you see, this is now sorted. So this is how heap sort works. We first do heapification of the array, meaning that we put it in the right order, we maintain it as a heap, and then we just apply get max n times. So this gives us the worst case of n log n time. So how many algorithms do you now know, sorting algorithms, that run in n log n time in the worst case? So we have merge sort, which runs in n log n time in the worst case. Is there any other algorithm that does that? Tree sort, right? If we keep the BST balanced, tree sort runs in n log n time in the worst case. And now heap sort, in the worst case, runs in n log n time. But the nice property of heap sort compared to merge sort and tree sort is that this is an in-place algorithm. We can actually just start from the array and not create another copy of it and get it sorted in n log n time, which is really great. Do you think this algorithm is stable? Why not? It is not stable because we are applying this swap operation. It's just like with selection sort. When you're moving things around without checking whether you need to move them around, you break the stability of the algorithm. Okay, so hopefully this gives you a bit of an idea of how heaps work, how priority queues can be implemented using binary heaps. Please leave your feedback in the feedback form. Please be constructive. My apologies for taking a long time to wake up. I know that I spent a long time in the first half of the workshop. And after that, please leave your feedback in the setu forms. We would really appreciate it. We need that. So if you go here, there will be a link to the setu survey. Every unit needs this, and our unit is not an exception. And please be constructive. I mean, obviously, every unit sucks, but please be constructive. how we can improve, how we can keep the unit good if you believe it's okay. And this is the penultimate workshop. You are almost there. Well done, people, and you are really great because you persevere and you wake up so early and make me wake up with you. So just one more week. Okay? So, well done, see you next week, and good luck with your assignment. Oh, by the way, don't forget to book your theory test session.